Bom dia, aqui é o Jean-Paul Brasselet e eu vou dar este curso sobre classes características no caso suave, de variedades suaves e também de variedades singulares. Antes, eu vou falar em inglês. Before starting, I would like to say two things. The first is that I will dedicate my course to Roberto Bedregal. Maybe you know that he's a professor in Jean Pessoa, and he died from the virus on 7th of April this year, and I dedicate my course to him. Also, I would like to say that I thank a lot many people who helped me for the course. In particular, Thuy Nguyen Tibish from UNESP in San José do Rio Preto, and many people who helped me. Okay, so this first course will be, as I told you, a cruise in time and a cruise through space as well. We will start the course in Greece, and we will go from Pythagoras to Poincaré. So the starting will be long time ago in 570 before Christus, and we will go to two places to start our cruise in Miletus, I think in English, and Samos. Samos is an island, and Miletus is here. This map is a map from Greece now, but at that time, all the coast, which is now in Turkey, all this coast here was Greece as well. So Miletus was in Greece. And you know maybe one guy from Miletus, which is Thales, Thales from Miletus, and he also, here is Thales. He born in 620 before Christus, and also Pythagoras of Samos, the island which is very near Miletus. I think they meet. Certainly, I think they meet. They have 50 years difference, but when Thales was 70, I think he met Pythagoras. Some people say that even Thales gave some advice to Pythagoras, and Thales was the guy who was able to evaluate the height of the height of pyramid in Greece, and so maybe they meet. Pythagoras was the first to give the description of three polyhedras, convex and regular. Regular means that all faces are the same, okay? And these three polyhedra was described by Pythagoras. Maybe we will take the boat now. We will continue our cruise we will go from Samos to Athens. We were here in this island of Samos, and we go to Athens, and more or less in 380 before Christus, and we take the boat going there from Samos to Athens. The boat is the one you have to row. So for the beginning of our cruise, you have to work. You have to row on this boat at that time. And in Athens, we meet a guy the name is Theaetetus of Athens. Theaetetus is very modern, as you can see. He is well in advance with his time because he is working on his computer. And Theaetetus was able to describe two more polyhedra regular and convex, which are icosaedra with 20 faces, and dodecaedra with 12 faces. Icosaedra with triangles, dodecaedra with a pentagon. Yeah, okay. And these 5 polyhedra, the one discovered by Pythagoras and the one discovered by Theaetetus, have been in fact described in Plato. By Plato. Plato was at the same time than Theaetetus, okay, contemporary. And Plato wrote Timaeus, and in this not a book, but he gives a description of the 5 polyhedra. Okay, so now we pursue our trip, our cruise, and we will go from Athens to Syracuse. You have to row again, and because we are now in 250 before Christus, and we are invited by somebody that you know as well, which is Archimedes. Archimedes invites us on the beach in Syracuse, in Sicily, and we play with him with these 5 polyhedra that we have already seen, 4, 6, 8, 12, and 20 faces. And Archimedes described more polyhedra, but they are not regular. As you can see, these sometimes are by truncature of the previous one, and these are described by Archimedes, but we will not be too much interested by this one, but to say that Archimedes described more of them. So as I said, we are in Italy, in Sicily, precisely in Syracuse with Archimedes, and we will stay for a long in Sicily from 250 before Christus to 1537 after Christus. And we stay in Sicily. You can see here Etna, which is a volcano, very active, still now, very active, and also Stromboli, which is an island, which is another volcano near Sicily. And we will go from Syracuse to Messina. During all that time, Sicily was was a property of many people. It was Greek at the beginning, then Roman, from people from Roma, then Germanic, Ostrogoth, it was Byzantine, Muslim, the Vikings came, Norman, French people, Swabian from Germany, Angevin from also France, Aragon, which is a part of Barcelona, and finally Spanish in 1537. Okay, so let's go from Syracuse to Messina. In Messina, I forgot to say, at that time, Brazil, 1534, that was the map of Brazil at that time, with divided horizontally and just with vertical. But very soon, Brazil was more or less definitive map from Brazil. But it's interesting to know that, okay, at that time. So that time is the time of Francesco Maurolico, Italian priest. And Francesco Maurolico was mainly playing or working, as you wish, with planar representation of these 5 polyhedra that we call Platonic polyhedra or Platonic solids sometimes. And he was trying to see what are all possible planar representation for this polyhedra. But this is what he liked to do. And he observed on December 26 in this year, 1537, just 2-3 lines in his manuscript in Latin, but I will translate for you. In the same way, it is evident that in each regular solid, the number of faces added to that of the vertices exceeds by 2 the number of edges. That is, consider a Platonic solid with V vertices, E edges, and F faces. We have the formula V minus E plus F equal to. That is something new that you don't see in books for the moment, because this appears in the thesis of Claudia Adabo, which she is an Italian researcher, and in her thesis in 2014, she gives this observation by Francesco Maurolico. In fact, Francesco Maurolico was the first to write this formula. It was for Platonic solid, not for all regular polyhedra, but already that is a scoop for the course, because you cannot see this in any book for the moment. All people say that Euler was the first one, but Maurolico did before. So this is very important. Well, we are now in 16, and we are here in Sicily, and that is the map of Europe at that time, which is absolutely not the map that you know now. It is well different, but you can see that at that time, Sardinia here and Sicily were Spanish, okay, and Italy was not unified, Germany was not at all unified, and so on. Okay, so but we will go from Sicily, and we will go to meet a guy that you know also very well, which is Descartes. And Descartes just arrived here in Stockholm. Descartes arrived in October 1649. He was going from France, not from Messine for me. And Descartes was invited by the Queen of Sweden, and we take a boat, which is much better. You don't need to row now to take this boat from Messine to Stockholm. That's good news. And Descartes wrote a theorem in more or less, we don't know exactly when he wrote this theorem, I think 1640, something like that, more or less. The sum of the angles of all faces of a convex polyhedron is equal to 2 v minus 2 p pi, where v is the number of vertices. And that is a very nice theorem. Descartes is very proud to show us this theorem. Just to recall to you, what is a convex polyhedron? There are two equivalent definitions. One is to say that if you take any 2 points inside the polyhedron, then the segment linking these 2 points is completely, entirely contained in the polyhedron. Another definition is to say that if you put the polyhedron on a surface, on a plane, if you put on a plane, the polyhedron will be completely on the same side of the plane containing the face. Okay, so these two are equivalent definitions for convex polyhedron. And the theorem of Descartes, here is an example of this theorem. You take all angles, for example, here I have a pentagon with 5 angles, triangle with 3, and a square with 4. I take the sum of these angles, also the one which are in the faces which are on the other side. Okay, you take the sum of all these angles, and this gives you 8, because you have 8 vertices, 8 minus 2 pi, which is 12 pi, the sum of it. So it's a very nice theorem by Descartes. Here is Descartes speaking with the Queen, Christine, the Queen of Sweden. She's on the left here. And this is maybe not exactly what they are speaking about, because the Queen asked Descartes to speak about philosophy, religion mainly, not too much mathematics. But she asked Descartes to come very early in the morning at 5 o'clock in the morning, and we are in winter, we are in October 1649. So it's winter, it's very cold, and Descartes used to awake at more or less 11, 12. So not at all at 5 in the morning. He was obliged to go very early, and we don't know if it's for this reason, but Descartes came illness very, maybe, not maybe, he was ill 4 months after arriving in Stockholm. We don't know if it is for cold. We don't know if it is because he was hosted by Chanu. Chanu was ambassador of France in Sweden, and Chanu had a pneumonia. And other people say that in fact Descartes was poisoned by a priest who was jealous of him, with an hostie. So we don't know. But what we know is that Descartes died on a February 11. You see, it's more 4 months after arriving in Stockholm. So he died very early, in fact. We are in Stockholm, and the our cruise will continue to Paris first, and then Hanover, which is here, and Berlin, which is here. In fact, we are in Stockholm with Chanu, with this guy, which is a French ambassador to Sweden, and he sent all Descartes manuscript by boat in a chest. So we take this boat with a chest, and he sent to Claude Clercellier. Clercellier was brother of wife of Chanu, brother-in-law, and he sent in Paris. Arriving in Paris, the boat sank in the river Seine. I hope you can swim, because we have to swim now. And but the chest was recovered 3 days later. But of course, it was full of water, and Clercellier dried the documents as best as he could. A little later, we are here in 1653, and a little later, 1672, Leibniz, that you know also, Leibniz, came to Paris. And Leibniz asked Clercellier to copy Descartes' manuscript, and Leibniz said, I will publish them as a Descartes manuscript. So he copied the Descartes manuscript, and he came to Hanover. We have seen on the map, Hanover. Okay, here, hop, here, Hanover. And he came to Hanover in 1676 with a copy of Descartes' manuscript. And Leibniz died in 1716 without publishing the manuscript. But we are now, so let's the manuscript for the moment, and we go to Berlin. We meet Euler. Euler wanted to classify convex polyhedra. He wanted to classify, and he thought the first, I will classify with the number of faces. Okay, so if I have 4 faces, 5, 6, 7, and number of faces. And yes, for example, hexaedra. So he look at convex polyhedra, but not regular. So they are faces are as you want. Okay, so hexaedra means 6 faces. If you have a polyhedra with 6 faces, okay, so that is a category, the number of faces, 6, and then he wants to distinguish them. And this Descartes thinks, okay, I will distinguish according to the number of vertices. So I have 1 with 5 vertices, 2 with 6, 2 with 7 vertices, and 2 with 8 vertices. So this gives me already a distinction, a classification. But there are 2 with 6 vertices, 2 with 7 vertices, and 2 with 8 vertices. So Euler thinks, okay, I will now distinguished with the number of edges. They are the same number of faces. For example, these two has the same number also of vertices, and I will distinguish with the number of edges. And Descartes calculate number of edges here and here. They have 10 edges. Oh, strange. So I will go to 7 vertices. I will distinguish these two. And the number of edges is 11 for both of them. Okay. And these two with 8 vertices, oh, they have 12 vertices, 12 edges. Two. So, and Euler sees that when you have the same number of faces and the same number of vertices, then the number of edges is the same. And in fact, the number of edges is number of faces plus number of vertices minus 2. So you have the Euler formula that is called Euler formula. Now it's for all convex polyhedron. You remember that Morelico gave it for the Platonic solid, the Platonic polyhedra, okay, which are regular. But Euler came to this formula. He wrote a letter in 1750 to his friend Christian Goldbach, and he wrote that it astonished me that the general property is not, as I know, it has not been noticed by anyone else before. It's very strange. But Euler did not know the Descartes theorem and did not know the Morelico manuscript. Clearly, he published 2 papers in which he described what he had done in more details and attempted to give a proof of the formula based on decomposing a polyhedron into simpler pieces. But this proof, they have some mistake in the proof, and he did not see all possibilities. So we will see now what happened coming back to Descartes, okay? Descartes and Euler. And we will see now that the Descartes theorem is equivalent to the Euler formula. So in fact, Euler formula is a consequence of the Descartes theorem we have seen before. I recall you the two, the Descartes theorem here, and the Euler formula here, okay? And we will see that the Descartes theorem implies the Euler formula. For that, we will compute the sum of all angles of all faces of a convex polyhedron in 2 ways. We know already one way, which is the Descartes theorem. The Descartes theorem says to you that the sum of all angles of all faces of the convex polyhedron is 2 times v minus 2 pi. Okay, this we know. And now, to go to the proof, we will denote by I going from 1 to f. F is the number of faces, okay? I goes from 1 to f. The 2-dimensional faces of the polyhedron. So we will denote 1, 2, 3, and we look at the number of vertices, Ki. Ki is also the number of edges for each face. For example, the face 1 have 5 vertices, also 5 edges. The face 2 has 4, the face 3 has 3, okay? So Ki here, Ki is the number of face of vertices, which is also the number of edges for each face, okay? Now, we know that a convex polygon with Ki edges can be divided in Ki minus 2 triangles. Okay? For example, if I have 5 edges, I can divide in 3 triangles. Now I know that in each triangle, the sum of all angles is pi. So as I have for a face of the polygon Ki minus 2 triangles, the sum of the triangles for this face is Ki minus 2 times pi, okay? And then I will make the sum of this for all edges, for all faces, sorry. So for one face, which Ki edges, the sum of angles is Ki minus 2 pi. So I make the sum of this for all edges, for all faces, I1 to F. Okay, this Ki minus 2 pi. So the sum for all faces is equal, I can distribute the sum here, so it gives me the sum of Ki minus 2F times pi. Okay, it's okay? Well, so we know also that each edge of the polygon appears in two faces. Okay, if you take a polyhedron, sorry, if you take a polyhedron, edge of the polyhedron, I will go to this polyhedron here, each edge appear in two faces. Each edge appear in two faces, okay? Okay, so the sum of Ki is equal to 2E. E is the number of edges, okay? So Ki is the number of edges for the face I, okay? And the sum of all of them appears twice, so 2E. No? So the sum of all angles of all faces is equal to 2E minus 2F times pi. If you use Descartes' theorem on this computation we did now, you find the Euler formula V minus E plus F equal 2. So, and you can go back in the proof, and in fact, this shows you that Descartes' theorem is equivalent to the Euler formula. Okay, so maybe it was written in the Descartes manuscript. We don't know for the moment. In the Descartes manuscript, we have seen the theorem. But the problem is that original documents have been completely lost, have been eventually lost. They came from people to people, and so they were lost. So the only one we have now, so Euler formula is 1751. The only one is a copy, Leibniz, but who cares of this? And in year 1883, so more than 100 years later, Fouché de Carrel, French ambassador to Austria-Hungary, he works a lot of publishing manuscript of Descartes and Leibniz. So he came in Hanover because he wanted to visit Leibniz's home. Aim was to see the Leibniz manuscript. And he discovered between the Leibniz manuscript, the copy of the Descartes manuscript that Leibniz copied when he was in Paris. And he said that he discovered this under the dust, the mountain of dust that covered all documents in this house 100 years later after the death of Leibniz. And Ernest de Foc de Jonquière, guy in Academy of Science, he published in Academy of Science in France the copy of the Descartes manuscript. He tells the story and he claims that Descartes discovered Euler formula. But it's true that Euler formula is not explicitly given in the copy of the manuscript that we have. Okay? So, okay, now we have to go to proof. As I said to you, Euler proof is not correct. So, who published proof of Euler formula? The proof of Euler is not correct. Later, Frances and Richardson make it possible to use, but well, later. In fact, the first complete proof is given by Legendre, and the first combinatorial proof by Cauchy. Some people say that the Cauchy proof is not correct, in particular Elon Lima, but with Thuy, Nguyen Thibish, we shown in a manuscript, we shown a paper which is published in 2020, that we can prove Euler formula using only the Cauchy method known at that time. Okay? So Poincaré is now waiting for us for the next step of our trip. I thank you very much for your attention. Thank you.